Imagine standing at the edge of the known universe. Not in a rocket, not in a spacecraft, just you, somehow suspended in the darkness, looking out across the cosmos. Below you, if below even means anything in space, stretches the familiar neighborhood of stars and galaxies, a billion points of light, each one a sun, many of them hosting worlds. Clusters of galaxies tangled together by gravity into enormous superstructures, strung like pearls along filaments of dark matter stretching for hundreds of millions of light years. It is magnificent. It is overwhelming. It confirms everything you ever thought about the universe, that it is full, that it is rich, that it teems with matter and energy and complexity on every scale. Now turn around. Not metaphorically, actually turn around in your mind's eye and look in the other direction. And there it is. Nothing. Not darkness in the way a night sky is dark, with stars you simply can't see. Not an emptiness waiting to be filled. Something else. Something that the human mind genuinely struggles to process because it contradicts every instinct we have about the universe. A void. A sphere of nothingness so vast that if you placed our entire galaxy, the Milky Way, with its 400 billion stars, at one edge and started traveling at the speed of light, you would travel for over 300 million years before you reached the other side. 300 million years at the speed of light. Let that sink in. The speed of light is approximately 300,000 kilometers per second. In 1 second, light travels a distance that would circle the Earth more than 7 times. In 1 year, light travels about 9.5 trillion kilometers, a distance we call a light year. The fastest spacecraft humanity has ever launched, the Voyager probes, would take over 70,000 years to travel a single light year. And this void is 300 million of those. Inside this void, where the mathematics of cosmic structure formation tells us there should be thousands upon thousands of galaxies, rich, complex, star-filled systems like our own, there are 60. 60. The cosmic equivalent of opening an encyclopedia and finding that 994 out of every 1,000 pages have simply been erased. In 2004, astronomers studying this region confirmed what earlier observations had suggested. This wasn't an error. It wasn't a gap in their data. The Bootes void, named for the constellation it sits behind from our perspective, is real. It is enormous, and by every standard cosmological model, it should not be quite as empty as it is. But here is what makes this discovery truly unsettling. It is not alone. Across the observable universe, the roughly 93 billion light-year sphere of space that light has had time to reach us from since the Big Bang, we have found thousands of these voids. Some are smaller, some are larger. Together, they account for an estimated 80% of the universe's total volume. 80%. Think about what that means. Every galaxy we have ever observed, every quasar we have ever detected, every signal we have ever received from the cosmos, all of it, every single scrap of observable matter and energy in the known universe is crammed into just 20% of available space. The remaining 80% is, by any ordinary measure, essentially empty. The universe is not what we thought it was. It is an ocean of nothing, threaded with thin filaments of something, and most of what we think of as the universe is, by volume, the exception rather than the rule. But recent observations have revealed something even stranger, something that is forcing cosmologists to tear up decades of assumptions. The voids may not be empty at all. What if they contain something invisible, something that isn't matter, doesn't emit light, doesn't interact with anything we can directly detect, but is nevertheless the dominant force shaping cosmic evolution? What if these vast regions of apparent nothingness are in fact the most energetically active places in the universe? What if the biggest mystery in all of cosmology isn't hiding in the brilliant blazing hearts of quasars, or the crushing singularities of black holes, or the violent collisions of neutron stars, but in the silence between them? Today, we journey through evidence that challenges everything we thought we understood about cosmic structure, dark energy, and the ultimate fate of reality itself. We will travel from the basement laboratories of Harvard University in the 1970s to the cutting edge of 21st century cosmology. We will meet the scientists who first mapped the cosmic web, confront the discoveries that broke their models, and follow the evidence into some of the most philosophically challenging territory in modern science. The universe is not what it seems. Prepare yourselves. We begin. For most of human history, when we looked at the night sky, we saw randomness. The stars appeared scattered without pattern, sprinkled across the celestial sphere like salt thrown carelessly across a dark tablecloth. Ancient astronomers grouped them into constellations: the hunter, the bear, the scorpion. But these patterns were accidents of perspective, two-dimensional projections of stars that were actually separated by enormous distances. The constellations aren't real structures, they're silhouettes. When the telescope was invented in the early 17th century, we began to see further. Galileo turned his crude instrument toward the Milky Way and discovered that what appeared to the naked eye as a diffuse band of light was actually composed of countless individual stars, too dim and too numerous to resolve without magnification. The universe was bigger than we'd imagined, but it still looked random. By the 20th century, we had established that the Milky Way was one galaxy among many, that the fuzzy smudges astronomers had cataloged for centuries as nebulae were in fact entirely separate star systems, some of them comparable in size to our own, separated from us by distances almost beyond comprehension. Edwin Hubble, working at Mount Wilson Observatory in California in the 1920s, measured the distances to several of these galaxies and made a discovery that reshaped the entire field of astronomy. The universe was expanding. Every galaxy was moving away from every other galaxy, as though the cosmos were a balloon being inflated from the inside. But crucially, and this is the assumption that would hold sway for the next 50 years, those galaxies appeared to be randomly distributed. Look in any direction and you'd find roughly the same density of galaxies. Point your telescope at the northern sky, you'd see approximately as many galaxies as if you pointed it south, or east, or west. The universe appeared isotropic, the same in all directions, and homogeneous, the same in all places. This was actually a good assumption, or at least a reasonable one. Einstein's equations of general relativity, when applied to the universe as a whole, worked most cleanly if you assumed matter was distributed uniformly. The mathematics of cosmic expansion were simplest in a homogeneous universe, and observation, with the limited tools of the mid-20th century, seemed to confirm it. Cosmologists developed elegant models of the universe based on this assumption. The Big Bang produced a hot, dense plasma that expanded uniformly. Matter condensed uniformly as the plasma cooled. Galaxies formed uniformly throughout the expanding space. It was a beautiful model. And then, Margaret Geller and John Huchra started mapping the universe in 3 dimensions, and the beauty shattered. In 1977, Margaret Geller joined the Harvard-Smithsonian Center for Astrophysics as a research fellow. She had a background in theoretical physics, but had become increasingly interested in observational cosmology, using telescopes to test the big ideas about how the universe was structured. John Huchra was already on staff, a tireless observer who had spent years cataloging galaxies and their properties. He had access to the telescope at the Fred Lawrence Whipple Observatory in Arizona, perched at an altitude of 2,300 meters in the mountains south of Tucson. Together, they embarked on what seemed, at the time, like a straightforwardly ambitious project. They would map a slice of the universe. Not just photograph galaxies, but measure their distances, and therefore their positions in three-dimensional space, by measuring their redshifts. Redshift is the cosmological equivalent of the Doppler effect for sound. When an ambulance drives toward you, its siren sounds higher pitched than it actually is, because the sound waves are compressed by the vehicle's motion. As it drives away, the pitch seems to drop, because the sound waves are stretched. Light behaves similarly. A galaxy moving away from us, which, due to cosmic expansion, essentially all of them are, has its light stretched toward the red end of the spectrum. The more distant the galaxy, the faster it recedes due to expansion, and the more redshifted its light appears. By measuring a galaxy's redshift, you can calculate its recession velocity. By applying Hubble's law, which relates recession velocity to distance, you can estimate how far away it is. It's not a perfect technique, because galaxies also have their own peculiar motions superimposed on the cosmic expansion, but for distant galaxies, it works remarkably well. Geller and Huchra set up a systematic survey. They chose a narrow strip of sky about 6 degrees wide, a thin slice of the cosmos, and planned to measure the redshifts of every galaxy brighter than a certain limit within that strip. The survey would take years. Each galaxy required a long exposure at the telescope, careful spectroscopic analysis, and precise measurement of redshift features. It was painstaking work. But as the data accumulated, something extraordinary began to emerge. The galaxies weren't randomly distributed. They formed patterns. Geller later described seeing it for the first time on a plot of the data. The galaxies arranged not uniformly, but in chains and sheets, outlining enormous bubble-like structures. She reportedly said it looked like the galaxies were arranged on the surfaces of soap bubbles, with the centers of the bubbles being empty. Soap bubbles. That image, immediately intuitive, immediately apt, would become one of the most famous analogies in cosmology, the cosmic web, a structure that once seen cannot be unseen. Geller and Huchra published their landmark results in 1989 in the journal Science. The paper, titled Mapping the Universe, presented the first clear, statistically robust evidence that galaxies were organized into a large-scale structure of filaments, walls, and voids. The centerpiece of their data was what became known as the stick man, a figure that appeared in their redshift survey maps. In the resulting diagram, galaxy positions plotted against redshift formed what unmistakably looked like a human figure with a stick body, created by the arrangement of galaxies along filaments. The cosmic web wasn't just a suggestion or a hint, it was visible, stark, and clear in the data. The paper triggered a revolution in cosmology. Other surveys rapidly confirmed the results. The universe had structure on scales far larger than anyone had previously demonstrated observationally. Galaxies weren't randomly scattered. They were organized, arranged in a cosmic architecture that bore no resemblance to the uniform soup of the Big Bang models. But confirming the existence of large-scale structure raised an immediate and troubling question. How did it form? The answer, which would take years to work out through a combination of observation and computer simulation, pointed to the earliest moments of the universe. In the first fractions of a second after the Big Bang, the cosmos was not perfectly uniform. Quantum fluctuations, the fundamental fuzziness of reality at the Planck scale, created tiny density variations, regions of space that were infinitesimally denser than average, regions that were infinitesimally less dense. These variations were extraordinarily small, variations of about 1 part in 100,000, but they were the seeds of everything. Gravity, operating over hundreds of millions of years, amplified these tiny differences into the enormous structures we see today. Denser regions attracted more matter, becoming denser still, and eventually collapsing into the galaxy clusters and filaments of the cosmic web. Less dense regions lost matter to their denser neighbors, becoming emptier and eventually becoming the vast voids. The cosmic web was, in a very real sense, a fossil record of the quantum universe, the subatomic fuzziness of the Big Bang, written in letters billions of light-years tall. But one feature of this structure was more surprising than any other. One aspect of the cosmic web that the early surveys flagged and that subsequent decades of observation would repeatedly return to was the voids. Not the filaments, not the clusters, not the great walls of galaxies, the nothing in between. Before Geller and Hutra's comprehensive survey, another astronomer had stumbled onto the void problem from a different direction. In 1981, Robert Kirshner, who would later become one of the leaders of the team that discovered dark energy, an achievement that earned his colleagues the Nobel Prize, was conducting his own galaxy survey with colleagues Augustus Oemler, Paul Schechter, and Stephen Schechtman. Their method was slightly different from Geller and Hutra's. Rather than surveying a continuous strip of sky, they sampled discrete directions, like core samples taken from soil, probing deep into the universe along narrow lines of sight. One of those lines of sight pointed toward a region of sky associated with the constellation Boötes. The team expected to find the usual distribution of galaxies, roughly proportional to the volume of space they were probing, with the numbers increasing at larger distances as the sampling volume grew. Instead, they found almost nothing. Over a distance range corresponding to what should have been a rich concentration of galaxies, the survey returned a striking absence, a gap, a region of space that appeared to contain far fewer galaxies than any cosmological model predicted. The team sat with this result for months, trying to explain it away. Surely it was an artifact of their sampling technique. Surely it was a statistical fluke, like getting 15 heads in a row when flipping a coin. You can get very unlikely results by chance, especially in small samples. But the statistics didn't cooperate. The probability of this void being a random fluctuation was, by their calculations, less than 1 in a million. They published their results in the Astrophysical Journal in 1981. The paper caused considerable excitement and some skepticism. Critics pointed out that the survey's sampling technique, those discrete core samples rather than a continuous strip, might be missing galaxies between the lines of sight. Perhaps the void was an artifact of the observing strategy. Further surveys addressed this criticism directly, deliberately pointing telescopes into the Boötes region to fill in the gaps. The void remained. If anything, the deeper surveys made it clearer and more well-defined. By the mid-1980s, the Boötes void was accepted as real, a roughly spherical region of space measuring somewhere between 250 and 330 million light-years across, with a galaxy density roughly 1/5 to 1/10 what cosmological models predicted. Kirshner, reflecting on the discovery years later, said that finding it felt like discovering a missing piece of the universe. A piece that was missing not in the sense that something had been removed, but in the sense that it had somehow never been there in the first place. That phrase is worth dwelling on. Not removed, never there. The Boötes void isn't an old filled region that has been emptied. It's a region that, as far as we can determine, never accumulated enough matter to form the density of galaxies that should be there. For reasons that trace back to those quantum fluctuations in the first microseconds of the universe, this particular region of space was always slightly less dense than average. And over 13 billion years, the gravitational mathematics amplified that slight deficit into one of the most profound absences in the known cosmos. We've been throwing around numbers, 330 million light-years, billions of galaxies, with the casual fluency of scientists who have become habituated to working at cosmic scales. But let's take a moment to actually sit with what these numbers mean, because this scale, truly understood, changes how you feel about the universe. The Milky Way, our home galaxy, is approximately 100,000 light-years in diameter. That means if you started at one edge and traveled at the speed of light, the absolute cosmic speed limit, the fastest anything can move, you would arrive at the other edge in 100,000 years. For context, human civilization is perhaps 10,000 years old. Modern Homo sapiens emerged roughly 300,000 years ago. The Milky Way is that old in light travel time. Now, the Boötes void is 330 million light-years across. That's 330 million divided by 100,000. Which means you could fit 3,300 Milky Ways lined up end to end inside the Boötes void. If you were somehow able to stand on one side of the void and look across to the other side, and if you had a telescope powerful enough to see individual stars, you would be looking at light that left those stars 330 million years ago. In 330 million years, the time it takes light to cross this void, the dinosaurs rose to dominance on Earth, ruled for 165 million years, went extinct, and were replaced by mammals. All of that happened in the time it takes light to cross one void. And there are thousands of voids. The giant void in the constellation Canis Venatici, discovered by astronomers in the 1980s, is even larger. Estimates put it at roughly 1.3 billion light-years across. That's 13 times the Boötes void. Light crossing the giant void would have departed before multicellular life had fully established itself on Earth. Together, all the voids in the observable universe account for approximately 80% of its total volume. This means that if you picked a random point in space, not a point in a galaxy, not a point near a star, just a genuinely random point in three-dimensional space, there's an 80% chance that point is inside a void. An 80% chance that point is in a region where galaxies are rare or absent. Most of the universe, by volume, is void. Think about what this means for how we typically imagine the cosmos. When we see photographs of deep space, the famous Hubble deep fields, for example, showing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, we tend to imagine the universe as crowded with galaxies. And in a sense, it is. The observable universe contains an estimated 2 trillion galaxies. 2 trillion galaxies, and yet they occupy only 20% of the available space. The rest is void.
A note of mystery enters the music. Something doesn't quite add up. Here is where the story becomes genuinely strange. The Boötes void should, according to standard cosmological models, be essentially empty. Not completely devoid of matter, the cosmic web has structures at all scales, including very tiny ones, but galaxies should be extremely rare. The chance fluctuations that seeded large voids should have produced very few high-density peaks inside them, meaning very few galaxies should have formed. But 60 galaxies exist inside the Boötes void, and they're not what you'd expect. These void galaxies are peculiar objects. They're smaller than typical galaxies. Many are what astronomers call dwarf galaxies, compact collections of a few billion stars compared to the Milky Way's several hundred billion. They're bluer than typical field galaxies, a property that indicates active star formation. Blue stars are young and hot and massive. They burn through their fuel quickly and don't live long. A galaxy that's still producing blue stars is a galaxy that's still forming new stars at a significant rate. This is strange. You might expect isolated galaxies in a void, cut off from the galaxy interactions and mergers that typically trigger star formation bursts, to be relatively quiescent, old, red, slowly fading. But many void galaxies show the opposite. They're actively forming stars. Some of the void galaxies show signs of recent interactions, twisted morphologies, asymmetric structures, tidal tails, streams of stars pulled away from the main body by gravitational forces, like taffy being stretched. These are the signatures you see when galaxies have recently encountered other galaxies. But there are no other galaxies nearby. Something isn't adding up. Three main hypotheses have been advanced to explain the presence and properties of void galaxies. The first hypothesis holds that these galaxies formed in place. Even within the underdense region of the Boötes void, there were local density enhancements, tiny pockets where matter was slightly more concentrated than average. Gravity amplified these local overdensities over time, eventually producing the conditions for galaxy formation. The void galaxies represent the rare, successful survivors of structure formation in an environment deeply hostile to it, like desert cacti, life finding a way in improbable conditions. The second hypothesis is more dramatic. The void galaxies are refugees. They originated in the denser regions of the cosmic web, in filaments or cluster outskirts, and were subsequently ejected by gravitational interactions. Close encounters between galaxies can be violent affairs, resulting in one or both participants being flung away at high velocity. Over millions of years, an ejected galaxy could travel hundreds of millions of light years, eventually coming to rest deep within a void. This hypothesis would explain some of the morphological oddities. A galaxy that recently experienced a violent interaction would show signs of disruption, exactly the tidal features and asymmetries observed in some void galaxies. And the timescales work. Given the ejection velocities typical of galaxy interactions and the ages of the structures involved, some ejections could have occurred early enough for the galaxies to have traveled the distances required. But the third hypothesis is the most unsettling of the three, because it removes the void galaxies from the center of the story entirely and makes the voids themselves the protagonists. The voids are growing. Not just existing, not just persisting, actively expanding, pulling matter toward their boundaries, growing over time, and as they expand, they engulf galaxies that once sat on their edges. Under this hypothesis, the void galaxies aren't anomalies within the void, they're remnants, stragglers left behind as the void's boundary swept past them. The void grew around them, leaving them stranded in the emptiness like desert island castaways, their supply lines to the rest of the universe cut off by the expanding ocean of nothing. This third hypothesis, it turns out, is substantially supported by computer simulations of cosmic evolution, and it introduces a concept that will come up repeatedly in this story. The void is not a passive absence. The void is active. It grows, it pushes, it shapes the universe around it.
Music builds toward transition, a cliffhanger moment. Standard cosmology, the lambda cold dark matter model that represents our best current understanding of cosmic evolution, predicts voids reasonably well. Simulations run on the world's most powerful computers, starting from the conditions of the early universe and running forward 13 billion years, produce cosmic webs with filaments, clusters, and voids. But the voids in the simulations don't quite match the voids we observe. They're the right size, roughly, they're in the right proportion, roughly, but the details are wrong. The expansion rates are off, the internal structures are different, the temperature profiles don't match, the galaxy populations inside are anomalous. And some of the voids we observe are simply too large to have formed in the time available, given what we understand about how structure grows under gravity. Standard cosmology shouldn't be able to produce a void like the Boötes void as often as we observe voids of that size. The numbers don't work. Which means either our measurements are wrong, or our models are incomplete, or something is happening inside voids that we don't yet understand. Something that the evidence forces us to confront, an uncomfortable possibility. Prepare yourself for Act 2. What we've covered so far is the discovery, the existence of voids, their surprising scale, the anomalous properties of the galaxies within them. But discovery is just the beginning of science. Discovery poses the question. Evidence is how we begin to find the answer. Over the past 4 decades, astronomers have brought an extraordinary array of tools to bear on the problem of cosmic voids. Radio telescopes, X-ray observatories in orbit, instruments sensitive to the faint microwave afterglow of the Big Bang, surveys mapping hundreds of millions of galaxies, computer simulations running on clusters containing hundreds of thousands of processors. Each of these approaches has revealed something different about voids. Each has added a new piece to the puzzle. And each new piece has, frustratingly, made the puzzle more rather than less complex. What follows is not an exhaustive catalog of void observations that would fill several academic textbooks. It's a curated tour of the most revealing, the most anomalous, and the most thought-provoking findings. The pieces of evidence that, taken together, suggest that voids are far stranger than empty space has any right to be. We begin with light, ancient light, from the very beginning of the universe.
In the year 380,000 after the Big Bang, the universe cooled enough for electrons and protons to combine into hydrogen atoms. Before that moment, the universe was opaque, a dense, hot plasma through which light could not travel freely. After that moment, it became transparent. The light that was released at that moment, the moment the universe first became transparent, still travels through space today. It's been traveling for 13.8 billion years, and it fills the entire sky. But because the universe has expanded so dramatically in the intervening time, that light has been stretched and cooled until it now falls in the microwave portion of the electromagnetic spectrum, invisible to human eyes. We call it the cosmic microwave background, or CMB. The CMB is the most perfect map we have of the early universe. Its temperature varies by tiny amounts from point to point in the sky, variations of only about 100 microkelvin or 100,000th of a degree. And those tiny temperature variations are the direct imprint of those primordial density fluctuations we mentioned earlier. The hot spots correspond to regions that were slightly denser in the early universe, the cold spots to regions that were slightly less dense. When we map the CMB in detail, which instruments like the WMAP satellite and the Planck satellite have done with extraordinary precision, we're essentially looking at a baby picture of the universe, taken when the cosmos was less than 1 million years old. Now, here's the thing. That ancient CMB light didn't travel directly from the early universe to our detectors in a straight line through empty space. It traveled through everything that subsequently formed,
through the growing cosmic web, through galaxy clusters, through filaments, and crucially for our story, through voids. And passing through these structures left marks on the light. The relevant physics is called the integrated Sachs-Wolf effect, named for the physicists Rainer Sachs and Arthur Wolf, who first predicted it in 1967. The mechanism works like this. CMB photons, particles of light, travel through the universe, gaining and losing energy as they move through the gravity wells created by large structures. When a photon falls into a gravity well, toward a cluster of galaxies, for example, it gains energy, blue shifting slightly. When it climbs back out, it loses that energy, red shifting. In a perfectly balanced universe where structures don't change with time, these effects cancel perfectly. Net energy change? Zero. But in our universe, structures do change with time. Galaxy clusters grow denser, filaments thicken, and voids expand. The gravity well changes shape while the photon is crossing it. If a void expands while a CMB photon is crossing, it has less gravitational well to climb out of than it fell into. It retains a tiny bit of extra energy, a tiny blue shift. Conversely, if a void expanded and the photon lost energy as it entered a steeper well, net effects compound. The critical point: measuring the integrated Sachs-Wolf effect allows us to detect the presence and behavior of voids using CMB light, completely independently of galaxy surveys. It's a way of probing the large-scale structure of the universe with a completely different instrument. When astronomers from teams at Princeton, Cambridge, and several European institutions analyzed the correlation between CMB temperature maps and galaxy distribution maps in the early 2000s, they found exactly the ISW signal expected in a universe dominated by dark energy. Photons passing through voids had gained energy compared to photons that didn't. The effect was tiny, just a few microkelvin of correlation signal, but it was statistically robust. The voids were real, and they were expanding. The dark energy signature was present. But in 2015, a team led by Andris Kovac of the Institute of Astrophysical Sciences in Budapest decided to push the analysis further. They cross-correlated void positions from the Dark Energy Survey, one of the most comprehensive galaxy mapping projects ever undertaken, with CMB temperature maps from the Planck satellite. They found a signal 4 times larger than theory predicted. 4 times. Not 4% more, 4 times. The ISW effect from the voids was showing up in the CMB with an amplitude that the best current cosmological models couldn't explain. Either the voids are more actively expanding than models predict, suggesting dark energy is stronger or behaves differently in underdense regions, or there's some other effect, some unknown physics operating inside voids that is imprinting additional temperature variations on the CMB. Or there's something wrong with the models themselves. The Kovac team published their results. The community responded with a mixture of excitement and caution. The measurement was provocative, but the systematic errors in combining CMB data with galaxy survey data are notoriously difficult to control. Subsequent analyses have confirmed the basic signal, but disputed its amplitude. The question remains open. But this represents just one piece of a much larger puzzle hidden in the cosmic web's evolution.
If voids are defined by the absence of galaxies, then the structures that define void boundaries deserve equal attention, and what structures they are. The boundaries of voids aren't gradual transitions. They're not slow, gentle increases in galaxy density as you move from void interior to normal space. They're sharp edges, regions where galaxy density changes dramatically over relatively short distances, and along these edges, galaxies concentrate into enormous thin structures called walls or sheets. The physics makes sense. As matter drains from void interiors, pulled by gravity toward denser regions, it doesn't simply vanish, it accumulates. Like water draining from a bathtub toward the drain hole, matter flows from void interiors toward void boundaries, and the boundary regions become overdense. The void is literally concentrating galaxies at its edges. The results of this process can be staggering in scale. The Sloan Great Wall, discovered in 2003 by J. Richard Gott and Mario Urich using data from the Sloan Digital Sky Survey, is a sheet of galaxies measuring approximately 1.37 billion light-years in length. It forms the boundary between several adjacent cosmic voids, separating emptiness from emptiness. It is, by some measures, the largest known structure in the observable universe. Or it was, until we found larger ones. The Hercules Corona Borealis Great Wall, detected in 2013 through observations of gamma-ray bursts, may span 10 billion light-years, making it the size of a significant fraction of the entire observable universe. If confirmed, it would represent a structure so large that it challenges the fundamental assumption of cosmology that the universe is statistically the same everywhere at large scales. A structure 10 billion light-years across isn't a local feature, it's a fundamental property of cosmic architecture. But the Great Walls aren't just big, they're thin. Astronomers have found walls spanning hundreds of millions of light-years in length and width, but only tens of millions of light-years in thickness. The aspect ratios are extraordinary, like continent-spanning sheets of paper, impossibly vast and impossibly thin. And they're not static, they show internal structure, filaments and knots within the sheets, smaller scale clustering superimposed on the large-scale geometry. They host galaxies that are themselves interacting and evolving. They are dynamic, complex, beautiful structures. But here's the anomaly. When astronomers carefully measure the orientations of the Great Walls, their angles relative to each other and to the void boundaries they define, they find something unexpected. The walls aren't randomly oriented. They show preferential alignments. The surfaces of voids across enormous distances tend to be oriented in correlated ways, as though shaped by some overarching structure or force that operates on scales even larger than the voids themselves. What could cause this? The leading hypothesis involves the gravitational influence of structures so large, so-called superstructures, or even the geometry of the universe on the Hubble scale, that their tidal forces shape void geometry across hundreds of millions of light-years. But this requires structures whose existence would be difficult to reconcile with standard cosmology. Something is organizing the voids. The identity of that something remains a genuine unsolved problem in modern cosmology. In mathematics, there's a beautiful and deeply strange concept called self-similarity. A fractal pattern, like the famous Mandelbrot set or the branching pattern of a fern, looks similar at every scale. Zoom in and you see the same patterns repeating. The structure doesn't simplify as you look closer. It continues, unresolved, all the way down. The cosmic web isn't perfectly fractal, but it has strong self-similar properties at certain scales. And when astronomers began mapping the interior of large voids with sufficient precision, they found something that immediately evoked this concept. Voids contain smaller voids. Inside the Botez void, careful surveys have identified several smaller underdense regions, voids within the void. These subvoids are perhaps 50 to 100 million light-years across, embedded within the larger structure like air bubbles within a larger bubble. And within the subvoids, there are hints of even smaller structures. This hierarchical structure, voids within voids within voids, is actually predicted by cosmological models, at least at small scales. Structure formation is hierarchical. Small structures form first, then cluster into larger structures. In underdense regions, small voids should form early, then merge and grow over time, leaving remnant smaller voids within larger ones. but the scale of the hierarchy observed in actual surveys is larger than simulations typically predict. The subvoids are more pronounced, their boundaries sharper, their interiors more evacuated than models produce. The most detailed analysis of subvoid structure comes from the 2-mass photometric redshift survey, which mapped galaxies across the entire sky using infrared observations. Infrared light penetrates dust clouds that block visible light, giving a clearer view of galaxy distributions. The resulting maps reveal a universe even more structured than optical surveys indicated, a cosmic web with fine structure all the way down to the resolution limit of the survey. Every void examined in detail shows internal complexity. Dark matter simulations suggest this complexity extends well below the scale we can directly observe, that even within voids, the dark matter forms a web of its own, just at much lower density. The void isn't empty even of dark matter. It's just that dark matter has its own hierarchy, its own web, a ghostly skeleton invisible to our telescopes, but present throughout. If true, and the evidence increasingly supports this, voids aren't empty spaces, they're underdense spaces, still participating in the cosmic hierarchy, still structured, just far less densely than the world we know.
In 2004, when the WMAP satellite released its most detailed map of the cosmic microwave background, the data showed something that stopped cosmologists in their tracks. In a region of sky corresponding to the southern constellation of Eridanus, there was a large cold spot. Not an artifact, not a measurement error, a genuine, statistically significant region of the CMB where the temperature was lower than the surrounding area by about 70 microkelvin. That might sound tiny, and in absolute terms it is. We're talking about temperature variations on a map where everything averages around 2.7 Kelvin above absolute zero. But in the context of CMB science, 70 microkelvin is enormous. The typical temperature variations in the CMB are around 100 microkelvin, and those represent the entire spectrum of primordial density fluctuations that seeded all the structure we see today. The cold spot wasn't predicted by any cosmological model. It was simply too large and too cold. For years after its discovery, astronomers debated explanations. Was it a statistical fluctuation, an unlikely but possible result of random variation? Some analysis suggested the probability was 1 in 150,000. Unlikely but not impossible. Was it an artifact of the data processing? Teams tried everything to make it go away, and it persisted. Was it the result of some foreground contamination, emission from gas or dust within our own galaxy, masquerading as a CMB signal? Careful multi-frequency analysis ruled this out. Or was there a physical cause? In 2015, astronomers at the Royal Astronomical Society published a study that suggested the answer. Istvan Saputty and his colleagues from the University of Hawaii analyzed galaxy survey data covering the Eridanus region and found exactly what the integrated Sachs-Wolf effect would predict: a large underdense region, a supervoid, aligned with the cold spot. The Eridanus supervoid measures approximately 1.8 billion light-years across. It lies at a distance of roughly 3 billion light-years from Earth, and it aligns with striking precision with the CMB cold spot. The integrated Sachs-Wolf effect that we described earlier, the tendency of CMB photons to lose energy as they pass through expanding voids, could in principle explain the cold spot. If a very large, very underdense region created a particularly strong ISW cooling signal, it would show up as exactly this kind of cold patch in the CMB. But here's the problem. Saputty's team calculated how much cooling a void of the Eridanus supervoid's measured size and density should produce through the ISW effect. The answer was about 20 microkelvin. The observed cold spot is 70 microkelvin. The supervoid is responsible for less than a third of the cooling observed. Something else is making the cold spot cold. This gap between the explained 20 microkelvin and the observed 70 microkelvin has become one of the most discussed anomalies in modern cosmology. On the more conservative end, perhaps the supervoid is larger, deeper, or differently shaped than the survey data suggests. Galaxy surveys have limitations. They don't see every galaxy, and their statistical power drops off at greater distances. The true supervoid might be more extreme than measured. On the more exotic end, the cold spot might represent the imprint of a collision between our universe and a neighboring universe in the multiverse. In the theory of eternal inflation, which we'll explore in detail later, the universe is one of an infinite number of bubble universes embedded in an eternally inflating space. These bubble universes occasionally collide. The collision leaves a scar in the CMB, a circular region of altered temperature. The cold spot is circular. It's the right size for a collision scar, and it's in the right direction relative to the CMB dipole, the large-scale temperature gradient caused by our galaxy's motion through space, for a collision to have been most likely. This is speculative. The collision hypothesis is consistent with the observations, but not uniquely supported by them. The cold spot might have a mundane explanation that our measurements haven't yet resolved. But it might not. And the fact that it might not is itself deeply significant. The most extreme void-associated structure we've found might be pointing us toward physics beyond anything currently in our textbooks.
Everything we've discussed so far involves voids at great distances. The Bode's void, hundreds of millions of light-years away. The Eridanus supervoid, 3 billion light-years distant. These feel abstract, remote, relevant to cosmologists, but not to ordinary life. But here is a discovery that changes the character of this story entirely. We live in a void. Not a metaphorical void, not a philosophical emptiness, an actual, measurable, cosmologically significant, underdense region of space. Our galaxy, the Milky Way, and all the galaxies we consider our nearest neighbors inhabit a region of space with significantly fewer galaxies than the cosmic average. This was first noticed in the 1980s by astronomers studying the large-scale distribution of galaxies in our immediate neighborhood. The local void, as it came to be called, measures roughly 150 million light-years across. The Milky Way sits near its edge, not at the center, but displaced, positioned on the boundary between the void's interior and the denser structure of the Virgo supercluster, the massive concentration of thousands of galaxies toward which we and everything in our neighborhood are slowly falling. The local void is, by the standards of cosmic voids, not particularly large. The Bode's void could swallow it several times over. But its significance is profound, because it means that every observation we've ever made of the universe, every measurement, every calibration, every test of cosmological theory has been made from inside a void. And voids, as we've been learning, are not typical environments. Here's why this matters practically. One of the most active debates in modern cosmology concerns the expansion rate of the universe, a quantity called the Hubble constant, denoted h0 or h0. The Hubble constant tells us how fast the universe is expanding, specifically how many kilometers per second a galaxy moves away from us for every megaparsec of distance between us. You can measure h0 in two fundamentally different ways. The first method works at small scales, the local universe, meaning within a few billion light-years. You find objects of known intrinsic brightness, Cepheid variable stars, type A1 supernovae, measure their apparent brightness as seen from Earth, and calculate the distance. Combined with the galaxy's recession velocity from redshift measurements, you get h0. This is called the local or direct measurement. The second method works at cosmic scales, using the cosmic microwave background. The patterns imprinted in the CMB reflect the physics of the early universe.
From those patterns, you can infer the expansion rate needed to produce today's cosmic structure. This is called the CMB, or early universe measurement. These two measurements should agree. They're measuring the same physical quantity. If cosmology is right, if the lambda cold dark matter model is correct, they should produce the same number. They don't. The local measurement gives approximately 73 kilometers per second per megaparsec. The CMB measurement gives approximately 67. The discrepancy is small in absolute terms, but at the level of precision these measurements have achieved, it's significant, a 5 sigma discrepancy, meaning the probability of it being a statistical fluctuation is roughly 1 in 3 million. Cosmologists call this the Hubble tension, and it's one of the most hotly debated problems in the field. Either one of the measurements is systematically wrong due to some unidentified bias in how distances are calibrated, or there's new physics involved. Here is where voids become relevant. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a paper arguing that we don't merely live in the local void, we live in a much larger underdense region they called the KBC void, named for their initials. Based on their analysis of galaxy counts in the two-mass survey, they proposed that the Milky Way sits inside a void roughly 2 billion light-years in diameter, roughly 6 times the size of the local void. If the KBC void is real, it changes everything about how we interpret our cosmological measurements. Inside a void, matter density is below average. Dark energy's effects are correspondingly stronger. The local expansion rate, the expansion rate we measure by observing nearby galaxies, would be higher than the global average because we're in a region where dark energy dominates more strongly. In other words, if we live in a void, the local Hubble constant would be higher than the CMB-derived Hubble constant. The universe would appear to us to be expanding faster than it actually is on average, which is exactly what the measurements show. The Hubble tension might not require new physics. It might require acknowledging that we're making our measurements from an unusual location, that we're surveying the universe from the bottom of a cosmic underdensity and getting a skewed picture as a result. It's a profound and humbling possibility. For centuries, science has worked to remove human bias from its measurements, to design experiments that don't depend on where you're standing when you make them. The Hubble tension might be telling us that we haven't succeeded, that our most fundamental cosmological measurements are contaminated by the accident of our location. The analogy that comes to mind is trying to measure the average altitude of a continent by standing in a valley. You'll get a reading and it'll be precise, but it won't represent the average. You need to know you're in a valley to correct for it.
Voids should be cold. This seems obvious. Temperature, in the astrophysical context, is related to the density and energy of gas. Void interiors have very little gas, or so we assumed, so they should be very cold. Measurements of the CMB temperature through voids confirm a slightly lower temperature than average, consistent with the ISW effect. But X-ray observations tell a different story. The Chandra X-ray Observatory and the European Space Agency's XM Newton satellite have been mapping the X-ray sky for decades. X-rays are produced by very hot gas, plasma, at temperatures of millions to hundreds of millions of Kelvin. Galaxy clusters, where gas is compressed and heated by gravitational potential energy, are the brightest X-ray sources in the sky. When astronomers turned X-ray telescopes toward void regions, they expected to find essentially nothing. A few foreground sources, perhaps, background sources visible through the void's relatively transparent interior, but not emission from the void itself. Instead, they found diffuse X-ray emission threading through what should have been empty space.
The signal is faint, far fainter than galaxy cluster emission, but it's real, and its properties reveal something astonishing. The gas emitting these X-rays inside voids is hot, very hot. Plasma at temperatures of tens of thousands to millions of Kelvin, far hotter than the void environment should naturally produce. Where does this hot gas come from, and how is it being maintained at such high temperatures in regions where there's almost nothing to heat it? This hot intergalactic medium inside voids is thought to be the warm hot intergalactic medium, or WIM, the missing baryonic matter that cosmologists have been searching for since the 1990s. When cosmologists account for all the matter in the universe, they find that visible matter, matter in stars and galaxies, accounts for only about half the normal, non-dark matter predicted by the CMB and by Big Bang nucleosynthesis. The other half should be somewhere, but where? The leading theory has always been that it's in a diffuse, warm gas between galaxies, the WIM, too hot to absorb visible light in a detectable way, too cold to emit strongly in X-rays under normal circumstances, too diffuse to form obvious structures, essentially invisible to all conventional astronomical instruments. Observations of void environments are now confirming that significant amounts of this WIM exist in void interiors. Models suggest voids may contain 20 to 40% of the universe's normal matter in this diffuse form. But the temperature is wrong. The WIM in voids is hotter than it should be if it's just ordinary gas left over from galaxy formation and expansion. Something is heating it. The leading candidates are dramatic: active galactic nuclei in void galaxies, supermassive black holes at their centers, periodically erupting and blasting enormous jets of plasma outward, and shocks generated by the expansion of the void itself. As the void boundary expands outward at hundreds of kilometers per second, it drives a shock wave into the surrounding medium, like the bow wave of a ship. This shock heats gas. But neither of these explanations fully accounts for the temperatures observed. The voids appear to be more energetic than models predict. Something is injecting energy into the void environment. The most remarkable discovery involves recent detections of gamma-ray emission from void regions, the highest energy form of electromagnetic radiation, typically associated with the most extreme events in the universe: gamma-ray bursts, blazars, magnetars. Finding diffuse gamma-ray emission from ordinary void environments is deeply unexpected. Whether this emission reflects dark matter annihilation, the process predicted by some dark matter models where dark matter particles collide and destroy each other, releasing energy, or some other exotic process remains under investigation. But the possibility of detecting dark matter through its energy signature in void environments has made voids one of the most exciting frontiers in high-energy astrophysics.
We've spoken about void galaxies in broad terms. Let's get more specific about what makes them unusual, because the details reveal something important about the relationship between environment and evolution. In the cosmic web, environment matters enormously. Galaxies in dense clusters, surrounded by hundreds or thousands of neighbors, evolve very differently from galaxies in sparse fields. Cluster galaxies tend to be elliptical, football-shaped blobs of old red stars with little ongoing star formation, their gas stripped away by collisions and gravitational interactions with neighbors. Field galaxies tend to be spiral, disc-shaped with ongoing star formation, maintaining their gas and building new stars. You might naively expect void galaxies to be extreme field galaxies, the most isolated, least disturbed systems in the universe. With no neighbors to strip their gas or disrupt their disks, they should form stars peacefully and maintain their spiral structure indefinitely. But observations complicate this picture.
Studies comparing void galaxies to equivalently sized field galaxies, controlling for mass and luminosity, consistently find that void galaxies are somewhat bluer and more actively star-forming than their field counterparts. This is the expected environmental effect. Less disruption means more gas available for star formation. But the difference is smaller than expected. If voids were simply extreme versions of low-density environments, void galaxies should form stars much more actively than field galaxies. The isolation should leave their gas supply untouched, their disks pristine, their star formation rates maximized. They don't show this. The difference between void galaxies and field galaxies is subtle, a trend, not a dramatic dichotomy. This subtlety is itself informative. It suggests that void galaxies are being shaped by something other than just their neighbor-free isolation. Something in the void environment is suppressing star formation relative to what a completely isolated galaxy would show. Candidates include the large-scale tidal forces from distant structures, the gentle gravitational tugging of filaments and walls hundreds of millions of light-years away, barely perceptible but cumulative over billions of years. These tidal forces might slowly distort void galaxies, disrupting their internal dynamics in ways that suppress star formation. Another candidate is the dark matter content of voids. If voids have their own dark matter substructure, small clumps of dark matter without visible galaxies, these subhalos would occasionally pass through void galaxies, generating tidal disturbances without visible traces. Void galaxies might be regularly disturbed by invisible neighbors, their evolution shaped by encounters we can't see. A 2020 study using data from the Mapping Nearby Galaxies at Apache Point Observatory survey found that void galaxies show higher rates of what astronomers call kinematic misalignment, cases where the rotation axis of stars in a galaxy doesn't match the rotation axis of the gas. This misalignment indicates past disturbances, interactions that twisted the galaxy's internal kinematics. In dense environments, such misalignment is common and easily explained by frequent galaxy interactions. In voids, it's harder to explain. But there it is in the data, suggesting void galaxies have experienced disturbances that their neighbor-free environment shouldn't have produced. Something is disturbing void galaxies. We just can't see what.
In 2007, Duncan Lorimer was reviewing archival radio telescope data from the Parkes Observatory in Australia when he found something extraordinary. Embedded in data from a 2001 observation was a flash of radio emission that lasted just a few milliseconds. In that brief instant, it released as much energy as the sun emits in several days, possibly weeks, and then it was gone. No repetition, no obvious counterpart at other wavelengths. The Lorimer burst, as it came to be called, was the first detection of what we now call a fast radio burst, or FRB. In the years since, astronomers have detected hundreds of FRBs using radio telescopes around the world. Some repeat irregularly, most don't repeat at all. Their sources span galaxies at distances of billions of light-years. Their physics remains one of the deepest mysteries in astrophysics. The leading explanation for most FRBs are magnetars, neutron stars with magnetic fields so intense that they make the strongest magnets ever built look insignificant by comparison. The energy released when a magnetar's magnetic field suddenly reorganizes, a stellar earthquake in essence, could plausibly account for the observed FRB energetics. In 2020, a burst from a magnetar within our own galaxy was detected, providing the first direct evidence connecting the two phenomena. But FRBs are cosmological tools as well as mysteries. As a radio burst travels from its source to our detectors, it passes through intervening gas. Higher frequency radio waves travel slightly faster than lower frequency waves through plasma, causing the burst to arrive at our telescopes with the frequencies spread out in time, higher frequencies first, lower frequencies later. This dispersion measure tells us how much plasma the burst has passed through, giving us information about the intergalactic medium along the line of sight. FRBs have been used to map the distribution of plasma between galaxies across billions of light years, a completely independent probe of the universe's large-scale structure. And this probe has revealed something unexpected. In 2020, a team led by Liam Connor and Vikram Ravi at Caltech published a study tracing a particular FRB, designated FRB 2019-0614A, to a galaxy deep within a cosmic void. The burst's properties were unusual. Its dispersion measure, the imprint of all the plasma it passed through, was lower than expected for a source at that distance, consistent with having traveled through less material than typical. This is expected for a void environment. The void is underdense, so there's less plasma to disperse the signal. But the degree of underdensity implied by the dispersion measure was larger than the galaxy survey data suggested for the void in question. Either the galaxy survey is underestimating the void's depth, there are fewer galaxies in that region than even the survey shows, or there's something about how radio waves travel through void environments that we don't understand. Subsequent analyses of multiple FRBs with sight lines crossing different void regions have found similar patterns. The dispersion measures suggest void interiors are slightly less filled with plasma than even our best models predict, which connects back to the temperature anomaly. If the hot gas in voids is concentrated in specific structures, thin filaments or sheets, rather than distributed uniformly, then lines of sight crossing the void's most underdense regions would encounter less plasma than average. The radio burst dispersion measures would be systematically low relative to models that assume uniform gas distribution. This paints a picture of voids with complex internal structure, not uniformly underdense, but threaded with invisible filaments of gas, punctuated by regions of near complete emptiness, not simply the absence of galaxies, but a structured, dynamic environment with its own architecture. What scientists discovered next would change everything about how we think about what fills empty space.
We have spent the past hour assembling pieces of evidence: the anomalous cold spot, the local void that biases our measurements of cosmic expansion, the hot gas that shouldn't be hot, the void galaxies disturbed by invisible neighbors, the FRB signals hinting at structure within emptiness. Now we step back, we look at the full picture, and we ask, what is actually going on? To answer that, we need to go back to the beginning. Not just the beginning of this story, but the beginning of the universe itself. Because cosmic voids, like everything else in the cosmos, have their ultimate origin in events that occurred in the first fractions of a second after the Big Bang. The universe began in a state of extraordinary density and temperature. In the first microseconds, the temperature was so high, in the range of quadrillions of degrees, that protons and neutrons hadn't yet formed from their constituent quarks. Matter and energy were inseparably intermingled. In this primordial state, quantum mechanics, the physics of the very small, played a fundamental role. Quantum mechanics is characterized by the Heisenberg uncertainty principle, which states that certain pairs of physical properties cannot be simultaneously known with arbitrary precision. Energy and time are one such pair. Position and momentum are another. One consequence of the uncertainty principle is that even the apparent vacuum, space with nothing in it, is not truly empty. It seethes with quantum fluctuations, pairs of virtual particles constantly blinking in and out of existence, borrowing energy from the vacuum for the briefest instants before annihilating each other and returning it. In the first moments of the universe, these quantum fluctuations were imprinted on the distribution of matter and energy. Regions where quantum fluctuations created brief concentrations of energy became slightly denser than average. Regions where fluctuations created momentary rarefactions became slightly less dense. The universe's initial conditions were not perfectly smooth. They were quantum fuzzy. The Big Bang, more properly called cosmic inflation, then dramatically amplified these tiny quantum fluctuations. In the inflationary epoch, thought to have lasted from roughly 10 to the minus 36th to 10 to the minus 32th seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th, 100 septillion times in a tiny fraction of a second. The quantum fluctuations, once subatomic in scale, were stretched to macroscopic sizes and frozen into the fabric of expanding spacetime. These frozen fluctuations became the seed of everything. The slight density variations in the early universe, 1 part in 100,000, that we see imprinted in the cosmic microwave background, represent the blueprint for the entire cosmic web. Every galaxy cluster, every filament, every great wall, every void, all of it was, in a sense, encoded in the quantum fuzziness of the very first moments. Yakov Zeldovich, the great Soviet physicist who contributed to some of the most important ideas in 20th century cosmology, developed the mathematical framework for understanding how these initial fluctuations evolved into the cosmic web we see today. His theory of gravitational instability showed how small density perturbations grow over time under gravity's influence. Overdense regions accrete matter. Underdense regions lose it. The Zeldovich approximation, as it's called, makes a striking prediction about the geometry of the resulting structure. Overdense regions don't simply collapse isotropically. They collapse first along one axis, forming sheets, then along a second axis, forming filaments, then finally along the third, forming compact clusters. The result is a web of sheets and filaments surrounding void regions, a structure that, in its broad outlines, exactly matches what Geller and Hutra found in their surveys. But Zeldovich's framework, brilliant as it is an approximation. It assumes the density perturbations are small enough that they can be treated linearly, each region evolving somewhat independently of its neighbors. In reality, structure formation is highly nonlinear. Neighboring regions influence each other's evolution through gravity. Dense regions pull matter away from their neighbors, creating secondary voids around them. Voids push matter toward their boundaries, accelerating the formation of walls. This nonlinearity means that the detailed properties of voids, their sizes, shapes, expansion rates, internal structures, cannot be predicted analytically. They require full numerical simulation.
Every simulation of cosmic structure formation, and there have been many, growing progressively more powerful as computing technology has advanced, requires one ingredient that has never been directly observed: dark matter. Dark matter is the most abundant form of matter in the universe. It outweighs ordinary baryonic matter, the protons, neutrons, and electrons that make up atoms, stars, and us, by a ratio of roughly 5 to 1. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way that we've detected. It makes itself known only through gravity. We know dark matter exists because of its gravitational effects. Galaxy rotation curves, the way stars orbit the center of their galaxies, don't match predictions based on visible mass alone. The galaxies rotate as though embedded in enormous spherical halos of additional invisible mass. Gravitational lensing, the bending of light from background sources by foreground mass, reveals dark matter halos around galaxies and clusters, visible through their gravitational effect on light, even though they're themselves invisible. Without dark matter, the cosmic web simply doesn't form. Ordinary matter alone doesn't have enough gravitational attraction to collapse into the dense filaments and clusters we observe. The universe would still be relatively uniform today, with little structure.
Dark matter provides the additional gravitational backbone, pulling matter together faster and at smaller scales. In the context of voids, dark matter's role is subtle but crucial. Computer simulations show that dark matter forms its own web, a ghostly skeleton underlying the observable cosmic web, and that this dark matter web persists even inside voids. Void interiors are not devoid of dark matter. They contain dark matter halos, concentrations of dark matter associated with galaxies and with what are called dark galaxies or dark halos, dark matter structures that never accumulated enough ordinary matter to form visible galaxies. These dark halos permeate void interiors. In a typical large void, simulations suggest there may be thousands of dark halos, potential galaxy sites that simply never acquired enough gas to form stars. They're there, exerting gravitational influence, but utterly invisible. The implications are striking. When astronomers observe the interior of a void and see only 60 galaxies, they're not seeing 60 isolated systems in a truly empty space. They're seeing 60 visible galaxies surrounded by thousands of invisible dark halos, all of them embedded in a low-density dark matter web. The void isn't empty, it's just dark. This dark skeleton might explain the morphological anomalies in void galaxies, the kinematic misalignments, the signs of past interactions. Void galaxies don't encounter other galaxies very often, but they do encounter dark halos, and dark halo interactions, while gentler than full galaxy-galaxy interactions, leave traces. Distortions in the stellar disk, triggered star formation episodes, kinematic offsets. The most recent simulations, the illustrious TNG and Eagle simulations run on some of the world's most powerful supercomputers, have sufficient resolution to track dark halo populations inside voids. The results confirm that void interiors are full of dark structure. Not as full as dense regions, obviously, but far from empty. The universe's dark skeleton reaches even into its emptiest regions.
Dark matter explains how structure forms, but dark energy explains how voids behave. Dark energy, discovered in 1998 through observations of distant supernovae by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, work that earned the three researchers the Nobel Prize in Physics in 2011, is the mysterious force causing the expansion of the universe to accelerate. It acts as a kind of anti-gravity on cosmic scales, pushing space apart rather than pulling it together. In its simplest form, dark energy is equivalent to what Einstein called the cosmological constant, a constant energy density inherent in empty space. It doesn't dilute as the universe expands because it's not matter. It doesn't get more spread out as the volume increases. It's a property of space itself. This gives dark energy a unique relationship with voids. In a high-density region, a galaxy cluster, dark energy is present, but overwhelmed by the gravitational attraction of the concentrated matter. Gravity wins. The cluster holds together. Dark energy's influence is negligible locally. In a void, a low-density region, the situation reverses. There's very little matter to generate gravitational attraction. Dark energy, operating uniformly throughout space, now faces minimal opposition. It dominates. The void expands faster than the surrounding universe. This means voids are, in a very real sense, the universe's best laboratories for studying dark energy. In dense regions, dark energy's signature is hidden beneath the gravitational chaos of matter interactions. In voids, it emerges cleanly. Cosmologists have recognized this for some time, and void surveys have become a major tool for constraining dark energy's properties. By measuring void expansion rates across cosmic time, comparing how fast voids were growing when the universe was young to how fast they're growing today,
researchers can track how dark energy's influence has changed, testing whether it's truly constant or whether it evolves. The current results are intriguing. When Anna Kovacs's team compared void abundances and shapes from the dark energy survey to predictions from dark energy models, they found that the data slightly favored models where dark energy's density decreases over time, an evolving dark energy, rather than a true cosmological constant. This is not conclusive. The statistical significance of the deviation is modest, but it's consistent with other hints from cosmological data that dark energy may not be as simple as Einstein's cosmological constant. If dark energy evolves, if its properties change over time, then void expansion rates in the past would have been different from void expansion rates today. The growth history of the cosmic web would have been different, and the largest voids we see today might have properties that reflect dark energy's evolution throughout cosmic history, preserved in their structure like rings in a tree trunk. This is the future of dark energy research, not just measuring the current expansion rate, but reading the evolutionary history of the universe's accelerated expansion from the precise shapes, sizes, and internal structures of its grandest voids. And then there's the question that the standard dark energy framework can't yet answer. Why is dark energy the strength it is? The theoretical prediction for dark energy strength, derived from quantum field theory calculations of vacuum energy, differs from the observed value by a factor of 10 to the power of 120. That's not a typo. 10 to the power of 120. This discrepancy, the vacuum catastrophe, is widely considered the largest unsolved problem at the intersection of quantum mechanics and cosmology. The answer to this discrepancy might lie in the properties of voids. If dark energy's strength is not a fundamental constant, but a dynamical field, something that evolves and responds to its environment, then its behavior inside voids might differ from its behavior in dense regions. Measuring that difference with sufficient precision could constrain theories of dark energy's nature in ways no other observation can. This forces us to reconsider fundamental assumptions about the most abundant component of the universe.
We stand at an extraordinary moment in the history of void science. The tools that have produced the discoveries we've described, the Sloan Digital Sky Survey, the WMAP and Planck satellites, the Chandra and XMM Newton X-ray observatories, represent the first generation of instruments truly capable of revealing the cosmic web in detail, but they are crude compared to what is coming. The next decade will bring a transformation in our ability to map and study cosmic voids, comparable in magnitude to the difference between Geller and Hutchgra's original pencil beam surveys of the 1980s and the Sloan Digital Sky Survey of the 2000s. The data we'll collect will be richer by orders of magnitude. The structures we'll resolve will be finer by similar factors. The conclusions we'll be able to draw will be correspondingly more profound. Let's walk through what's coming. The Vera C. Rubin Observatory in Chile, named for the pioneering astronomer who provided some of the most compelling early evidence for dark matter, began its legacy survey of space and time in 2025. Over 10 years, its 8.4-meter mirror and 3.2 gigapixel camera, the largest digital camera ever built for astronomical purposes, will photograph the entire southern sky approximately every few nights. The result will be a movie of the sky, not a static snapshot, but a dynamic record tracking the positions and brightnesses of billions of objects across a decade. For void science, this translates to maps of unprecedented depth and completeness, covering billions of galaxies and enabling the identification of voids across a range of cosmic scales and distances that no previous survey has approached. Crucially, the Rubin Observatory will track how voids evolve over time. By observing the same regions of sky at intervals of days, months, and years, it will capture the movements of galaxies at void boundaries, directly measuring how void walls expand and how galaxies fall toward them. This kinematic data will constrain void dynamics in ways that static maps cannot. The Nancy Grace Roman Space Telescope, planned for launch in 2027, will complement Rubin with its infrared capabilities. Operating above Earth's atmosphere, Roman will observe wavelengths of light blocked by the atmosphere, seeing through dust clouds that obscure optical surveys. It will also observe further into the universe, mapping large-scale structure at higher redshifts, looking further back in time to the universe when it was younger. Roman will measure weak gravitational lensing across its survey volume. Weak lensing, the slight distortion of background galaxy shapes by foreground mass, responds to all mass, visible and dark, unlike galaxy surveys that only trace visible galaxies. Roman's lensing maps will reveal the dark matter distribution inside voids, testing whether the dark halos predicted by simulations are actually present and in the quantities expected. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is already producing its void science results. Euclid will map the shapes and positions of billions of galaxies out to redshift 2, when the universe was roughly 3 billion years old, in both visible and near-infrared light. Its primary science goals include measuring how cosmic structure grew over time and testing whether dark energy evolves. Void catalogs from Euclid will be among the most powerful constraints on dark energy yet obtained. The shapes of voids, which respond differently to different dark energy models, will allow researchers to distinguish between cosmological constant dark energy and evolving dark energy models with a precision that no previous survey has achieved. The Square Kilometre Array, currently under construction in South Africa and Australia, will bring radio astronomy to bear on void science at unprecedented sensitivity. The SKA will detect 21-centimeter emission from hydrogen gas, the most abundant ordinary matter in the universe, across cosmic distances. This will allow direct mapping of the neutral gas content of void interiors, revealing the distribution and temperature of the intergalactic medium in ways currently accessible only through X-ray and ultraviolet observations. The SKA will also dramatically expand the FRB catalog. Currently, FRBs number in the hundreds of confirmed events. The SKA is expected to detect thousands of FRBs per day. This statistical sample will enable precise mapping of the intergalactic medium along thousands of sightlines, building a three-dimensional picture of ionized gas distribution throughout the cosmic web, including, crucially, through void interiors. Recent breakthroughs suggest that gravitational wave astronomy will also contribute to void science. The LISA mission, the Laser Interferometer Space Antenna, planned by the European Space Agency for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers across the universe. Some of these mergers will occur in void galaxies, and the properties of the gravitational waves, how they are distorted by propagating through different cosmic environments, will provide information about the space-time geometry of voids. All of these missions, working together, will transform void science from an observational curiosity into a precision cosmological tool.
The scientific community's growing interest in voids as cosmological laboratories isn't simply intellectual curiosity. It's driven by a specific and urgent need. We need to understand dark energy. Dark energy constitutes 68% of the universe's total energy content. It determines the ultimate fate of everything that exists. It controls whether the universe expands forever, whether it tears itself apart in a big rip, or whether some unknown future physics reverses the expansion and brings everything back together. And we have essentially no idea what it is. The cosmological constant interpretation that dark energy is an intrinsic energy of empty space is mathematically consistent but physically unexplained. Quantum field theory can't account for its value. General relativity requires it but doesn't explain it. String theory produces a landscape of possible values but can't predict which one our universe inhabits. Alternative interpretations proliferate. Quintessence models propose that dark energy is a dynamical field, something that evolves over time, like the Higgs field that gives particles mass, but pervading all of space and slowly changing in its properties. Modified gravity theories propose that dark energy isn't a substance at all, but a manifestation of gravity behaving differently at large scales than Einstein's equations predict. Interacting dark energy models propose that dark energy and dark matter, usually treated as completely separate entities, interact with each other through non-gravitational forces. Each of these alternatives makes different predictions for how cosmic structure grows over time, and specifically for how voids behave. Quintessence dark energy would cause voids to evolve differently than cosmological constant dark energy. Modified gravity would alter the shapes of voids and the motion of galaxies at their boundaries. Interacting dark energy would change the relative distributions of dark matter and dark energy inside voids. This is why void science has become a priority for the next generation of surveys. Voids are distinguishers. They can tell apart dark energy models that look identical in their effects on galaxy clustering or CMB power spectra. The void is the most sensitive probe of dark energy in the universe's toolkit. A research program led by Will Percival at the University of Waterloo and Alice Pisani at Princeton University has developed rigorous statistical methods for extracting dark energy information from void catalogs. Their methods, the Alcock-Paczynski test applied to voids, the void size function, the void density profile, are now standard tools in the field. Preliminary results from the Dark Energy Spectroscopic Instrument, or DESI, which began its survey in 2021 from the Kitt Peak National Observatory in Arizona, are already providing the most precise void-based constraints on dark energy ever obtained. DESI will ultimately map tens of millions of galaxies and identify hundreds of thousands of voids, providing data sufficient to distinguish between major dark energy models at high statistical significance. The answer to one of science's deepest questions might be hiding in the universe's empty spaces.
To properly understand void science, you cannot separate it from the revolution in computational cosmology. Modern cosmology is a field where theory, observation, and simulation are intertwined in ways unprecedented in the history of science. We cannot analytically solve the equations governing cosmic structure formation. The nonlinear interactions are too complex. We cannot observe the universe evolving in real time. The timescales are too vast. Instead, we simulate. The Millennium Simulation, completed in 2005 by Volker Springel and colleagues at the Max Planck Institute for Astrophysics, was one of the first simulations capable of reproducing the cosmic web in detail. It tracked the evolution of 10 billion dark matter particles in a cube of space 685 million light-years on a side, from the early universe to the present day. The result was a simulated universe with filaments, clusters, and voids that statistically matched observations remarkably well. The Millennium Simulation was followed by increasingly ambitious projects. The Bolshoi simulation, the dark sky simulations, the multi-dark simulations. Each generation brought more particles, larger volumes, higher resolution, more sophisticated physics. The most recent large-scale simulations track trillions of particles in volumes tens of billions of light-years across. These simulations have been invaluable for void science. They produce synthetic void catalogs that can be compared directly to observational data, testing whether our theoretical models of void formation and evolution are correct. When simulations and observations agree, we gain confidence in our understanding. When they disagree, we have identified a clue. The disagreements are the interesting part. As we've noted throughout this documentary, void observations consistently produce results that deviate from simulation predictions at a statistically significant level.
Void abundances, the number of voids of each size, are slightly off. Void expansion rates don't quite match. The cold spot is too cold. The galaxy population inside voids is wrong in subtle but consistent ways. Some of these disagreements might reflect limitations of the simulations. Baryonic physics, gas, star formation, supernova feedback, black hole growth is enormously complex and incompletely included in current simulations. Some might reflect systematic errors in the observations, calibration uncertainties, selection effects, incompleteness in surveys. But some might reflect genuine failures of the theoretical model. The lambda CDM model might be wrong, or at least incomplete, in ways that most clearly manifest in void environments, where dark energy dominates and our assumptions about its nature matter most. The next decade's simulations, using next-generation supercomputers like the proposed exascale facilities in the United States and Europe, will be powerful enough to test this directly. Simulations including all known physics at sufficient resolution to predict void properties in detail will be compared to the Rubin, Roman, Euclid, and DESI observations. Agreement will confirm the model. Persistent disagreement will demand revision. And revision in science is not failure, it's progress. We have now traveled in our minds from the basement laboratories of Cambridge, Massachusetts in the 1970s through the great walls and supervoids of the cosmic web, past the quantum seeds of emptiness planted in the first fractions of a second of the universe's existence, and into the future where new telescopes and simulations promise to crack open the deepest mysteries of dark energy. It is time to ask the questions that physics alone cannot fully answer, the questions that live at the border between cosmology and philosophy, the questions that, once asked, cannot be unasked. What is a void? Not in the technical sense, we've covered that thoroughly, but in the deeper sense, what does it mean for space to be empty? What is the ontological status of a region of the universe where nothing, or almost nothing, exists? In everyday life, nothing seems like the simplest possible thing, the most fundamental absence. Empty space is space where there's nothing, no objects, no substance, no content. But modern physics has decisively destroyed this intuition. Even in the most evacuated region of a cosmic void, a region of space that would be considered a near-perfect vacuum by any engineering standard, something is happening. Quantum field theory tells us that space is not emptiness, but a seething sea of quantum fields. The electromagnetic field, the Higgs field, the quark fields, the lepton fields, the gluon field. All of these fields pervade every point in space, even in the deepest void, and all of them fluctuate constantly, their quantum fluctuations generating virtual particles that blink into existence for instants so brief they cannot be directly observed. This quantum vacuum is not nothing. It has energy, the zero-point energy predicted by quantum mechanics for any field in its lowest energy state. And this vacuum energy, summed over all quantum fields, should be enormous, far larger than the observed dark energy density. The mismatch between the theoretically predicted vacuum energy and the measured dark energy density is the vacuum catastrophe we mentioned earlier, the largest known discrepancy between theory and observation in all of physics. But let's set the vacuum catastrophe aside for a moment and focus on a different aspect of quantum fields in voids. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience a tiny attractive force between them. The reason, the quantum fluctuations between the plates would be restricted to certain wavelengths, while the fluctuations outside the plates would not be similarly restricted. The result would be a slight difference in vacuum energy between the inside and outside, a difference that would push the plates together. The Casimir effect has been measured experimentally.
It's real. Two metal plates in a vacuum are pushed together by the energy of nothing. Now, cosmic voids have boundaries, the walls of galaxies that define their edges. These boundaries impose constraints on the quantum fields inside the void, analogous to the metal plates in the Casimir effect. Different constraints operate on different scales, but the principle holds. The quantum vacuum inside a void might differ from the quantum vacuum outside it. The energy of emptiness might vary depending on what surrounds it. If this is true, and it's speculative beyond the current frontier of theoretical physics, then void boundaries are not just geometric features of the cosmic web, they're physical boundaries that affect the quantum properties of space itself. The void interior has a quantum structure that's different from the quantum structure of dense regions. This would mean that dark energy, if it's related to vacuum energy, would indeed vary spatially, stronger or weaker in voids compared to dense regions. And this spatial variation might be precisely what the void expansion rate anomalies are measuring. We might be seeing quantum physics operating at cosmological scales, the Casimir effect writ enormous, the boundaries of cosmic voids shaping the energy of the vacuum within them. Consider this. The universe's structure, from the quantum fuzz of the Big Bang through the cosmic web to the Casimir-like effects at void boundaries, it's quantum mechanics all the way down and all the way up. Think about that. In 1950, the physicist Enrico Fermi posed a simple question during a lunch conversation at Los Alamos National Laboratory. If intelligent life is common in the universe, if the conditions for life exist around billions of stars in billions of galaxies, then where is everybody? The universe is ancient. If even a single civilization had achieved interstellar travel and the drive to colonize, they would have had billions of years to spread across the galaxy. By any reasonable calculation, signs of their existence should be ubiquitous, and yet, silence. This is the Fermi paradox, and while it's usually framed in terms of our own galaxy, where are the aliens, it applies with even greater force to the cosmic web. Consider the void galaxies. We've established that some galaxies exist deep within cosmic voids, isolated systems, their nearest galactic neighbors hundreds of millions of light years away. If any of these void galaxies harbors intelligent life, that civilization faces an extraordinary situation. From inside a void galaxy, the night sky would be dramatically different from our own. Our galaxy is surrounded by dozens of nearby galaxies. The Andromeda galaxy is visible to the naked eye. From a void galaxy, the nearest large galaxy might be so far away that it's invisible without a telescope, or barely visible as the faintest smudge on the sky. The universe from a void galaxy would appear to consist of your own galaxy, and then essentially nothing. What would a void civilization's cosmology look like? They might discover that the universe contains exactly one galaxy, their own. The rest of the observable universe, for all practical purposes, would appear empty. Their equivalent of Edwin Hubble, scanning the sky with their equivalent of a 100-inch telescope, would find no nebulae to resolve into galaxies. Their universe would seem to consist entirely of their home galaxy, surrounded by infinite emptiness. They would develop a very different cosmology, perhaps one without the concept of galaxies as building blocks of the universe, since they'd see only one example. Perhaps without any understanding of the cosmic web, which would be invisible from their position in the void's interior. Perhaps without any recognition that they inhabit a cosmologically unusual location. Their physics might be the same. Quantum mechanics and general relativity don't care whether you're in a void or a cluster, but their interpretation of the universe's large-scale structure would be profoundly different from ours. When we detected the cosmic microwave background in 1965, it immediately revealed that the universe had a specific history, a hot, dense beginning that cooled over time. A void civilization would also detect this background because it permeates all of space, but their interpretation of its features might differ from ours.
Without nearby galaxies to correlate with CMB temperature variations, the large-scale structure information encoded in the CMB might be harder to interpret. And here's the most sobering aspect of this thought experiment. Communication between void civilizations and civilizations in the cosmic web would be extraordinarily difficult. Even if a void civilization beamed a radio signal at the Milky Way, knowing somehow that we existed hundreds of millions of light years away, that signal would take hundreds of millions of years to reach us. By the time it arrived, the void civilization might have been extinct for longer than modern humans have existed. The Fermi paradox applied to void civilizations reveals a universe so vast and so structured that even intelligence might not be able to bridge its gaps. The cosmic web creates connections among civilizations in dense regions. Cosmic voids create insurmountable isolation. If the universe contains void civilizations, and there's no reason it shouldn't if life is anything close to common, then those civilizations are, for all cosmological purposes, alone. Their universe contains one galaxy, their history involves no contact with the broader cosmos, and they might be entirely unaware that most of the universe is void, just as we almost were.
In 2003, philosopher Nick Bostrom published a paper in the Philosophical Quarterly that has since become one of the most widely discussed thought experiments in science and philosophy. His argument, known as the simulation hypothesis, goes roughly like this. Consider three possibilities. Either the vast majority of civilizations go extinct before they develop the computational power to run realistic simulations of universes, or the vast majority of civilizations that do achieve this capability aren't interested in running such simulations, or we are almost certainly living in a computer simulation right now. The argument depends on the observation that a sufficiently advanced civilization with sufficient computing power could run arbitrarily many simulated universes containing simulated beings with simulated consciousness. If even one such civilization exists and runs a large number of simulations, the number of simulated minds would far exceed the number of real minds, and we would have no way to know whether we were among the real ones or the simulated ones. This is philosophy, not physics, but it becomes relevant to void science when you ask a specific question. If our universe is simulated, how would you simulate it efficiently? Computing a simulation of a universe is extraordinarily demanding. Every atom in every galaxy, every quantum field fluctuation in every cubic meter of space, simulating all of it in real time would require computational resources that dwarf anything imaginable. A civilization running such a simulation would presumably want to use computational resources efficiently. One obvious economy: simulate regions of the universe in detail only when they're being observed, or only when they're important for the simulation's narrative. Background regions, regions that have no observers and no significant events, could be computed less precisely, stored in a simplified form, or not computed at all until they become relevant. Cosmic voids, by this logic, are exactly the kind of region that a simulation economy might deprioritize. They have few galaxies, few observers, few events of cosmological significance. They could be represented as empty in the simulation's internal representation, approximated rather than fully computed. If this were the case, you might expect void regions to show subtle anomalies compared to theory, regions where the simplified representation breaks down, where the approximation produces results inconsistent with the fully computed dense regions, void expansion rates that don't quite match, internal temperatures that are slightly off, galaxy populations that are subtly wrong. I want to be clear, I am not claiming our universe is simulated. The simulation hypothesis is not a scientific theory. It makes no specific, testable predictions. But it is interesting that the anomalies we find in void observations have exactly the character you'd expect from a computational approximation breaking down.
The regions that should be simplest, the empty ones, are the ones producing the most persistent anomalies. Make of that what you will. But here's a more grounded version of the same observation. Even without the simulation hypothesis, there's something deeply significant about the fact that our understanding of the universe is most uncertain precisely in the emptiest regions. Voids, which might seem like the most straightforward thing to model, after all, there's barely anything there, are the regions where our models most consistently fail. The nothing is harder to understand than the something.
Let us project forward now, not 1,000 years, not 1,000,000 years, but across time scales that make the current age of the universe look like an eye blink. At the present epoch, 13.8 billion years after the Big Bang, the cosmic web is in what cosmologists sometimes call its golden age. Large-scale structure has had time to develop into its current complexity. Magnificent filaments, rich galaxy clusters, grand voids. But the universe has not yet been so dominated by dark energy that these structures are fragmenting into isolation. We live, in other words, at the perfect moment to be cosmologists. We can see the full sweep of cosmic structure, nearby galaxies, distant quasars, the cosmic microwave background from the universe's infancy. The cosmic web is visible and interpretable in all its glory. This window will not remain open forever. In roughly 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, rendering Earth uninhabitable. But even before that, on longer timescales, the cosmic landscape will begin to change in ways that would profoundly alter any surviving civilization's understanding of the universe. As dark energy continues driving accelerated expansion, the distance between galaxy groups will grow. Galaxies currently in the cosmic web, connected by filaments to their neighbors, will slowly lose those connections as expansion stretches the filaments to the breaking point. The cosmic web will begin to dissolve. Within 100 billion years, roughly 7 times the current age of the universe, most galaxy groups outside our local group will have receded beyond our cosmological horizon. The expansion between us and them will exceed the speed of light, and their light will never reach us again. They will vanish from our observable universe, not by moving, but by the space between us expanding faster than light can cross it. From that point forward, a civilization in our local group would observe a universe that appeared to contain only a few dozen galaxies. The thousands of galaxy clusters, the millions of filaments, the great cosmic web, all of it would be beyond the horizon, invisible, unreachable. Now go further, 1 trillion years, 10 trillion, 100 trillion. Stars exhaust their fuel. The Milky Way and Andromeda, after merging in a collision expected in about 4 billion years, gradually consume their star-forming gas. New star formation slows and eventually stops. The existing stars age. The red dwarfs, which are the most common type and the most long-lived, will burn for 10 to 100 trillion years before fading to cold, dark remnants. 100 trillion years from now, the last red dwarf star dies. The cosmic web, what remains of it within any surviving civilization's horizon, consists of cold, dark remnants, white dwarfs slowly cooling, neutron stars gradually radiating away their heat, black holes still present, their event horizons locked, their masses slowly evaporating through Hawking radiation on timescales of 10 to the 67th to 10 to the 100th years, depending on their mass. The universe is becoming a void. Not one void, not a web of voids. The universe itself is transforming into a state indistinguishable from the interior of a cosmic void as we know it today. Cold, dark, expanding, nearly empty. The voids we study now, in this sense, are harbingers. They are previews of the universe's ultimate destiny. By studying void environments, by understanding the physics of regions where dark energy dominates and matter is scarce, we are studying the state toward which all of existence is inevitably heading. This realization carries a strange philosophical weight. We tend to think of the cosmic web, the galaxies, the stars, the planets, the life, as the important stuff, and the voids as the background against which it plays out. But in terms of the universe's evolution over time, it's the voids that are the destination. Structure, what we call the cosmic web, is a transient phase. A beautiful, complex, remarkable phase that happens to be where we exist, but transient. The philosopher Blaise Pascal wrote in the 17th century, "The eternal silence of these infinite spaces frightens me." He was writing about the night sky, but he might as well have been writing about the heat death, the ultimate void future that modern cosmology has revealed. We have two responses to Pascal's fear. One is existential despair. The other is wonder. We happen to exist at the precise moment in cosmic history when the universe is most complex, most interesting, most beautiful. Billions of years of structure formation have produced stars, planets, and the minds capable of asking why. Before us, a quantum fuzz of near uniformity in the early universe. After us, an expanding sea of cold darkness. Right now, this, a universe full of light. What scientists discovered in studying the voids is that the fullness we inhabit makes the most sense against the background of what surrounds it.
We began with a void. We began with Robert Kirshner's team pointing their telescope at a region of sky in the constellation Boötes, expecting to find galaxies, and finding almost none. We began with a discovery that the universe, in this particular corner of its vast extent, had simply chosen not to fill itself with matter. And over the course of 3 hours, we have followed that emptiness wherever it leads. We followed it to Margaret Geller and John Huchra's basement laboratory at Harvard, where the cosmic web first revealed itself in all its strangeness. A universe organized not randomly, but into a foam of filaments and bubbles, with the bubbles occupying most of the volume. We followed it to the Eridana supervoid and the cold spot, a wound in the microwave sky that is too cold by a factor of 3, pointing toward physics our best models cannot yet explain, and perhaps toward evidence of a multiverse beyond our own. We followed it inward to our own local void, the underdense bubble in which the Milky Way resides, and which may have been biasing our measurements of the universe's expansion rate for decades without our realizing it. The Hubble tension, that persistent 5 sigma disagreement between two of cosmology's best measured quantities, might be our own cosmic address distorting our cosmic census. We followed it to the X-ray observatories, which found the void interiors not dark and cold as expected, but threaded with hot, inexplicably energetic gas. We found that voids contain 20 to 40% of the universe's ordinary matter in forms previously too diffuse to detect, a warm intergalactic medium hiding in the apparent emptiness. We followed it to the void galaxies themselves, those 60 inhabitants of the Boötes void, and their counterparts in thousands of other voids across the observable universe. These strange, isolated systems with their active star formation, their morphological disturbances, their kinematic misalignments that speak of encounters with invisible dark matter halos. Galaxies shaped by neighbors that cannot be seen. We followed it forward in time to a future where dark energy continues driving cosmic expansion, where the cosmic web fragments into isolated islands, where each galaxy group becomes its own private universe surrounded by a void that expands faster than light.
a future where the cosmic archival imperative, if any civilization survives to heed it, demands that we record what we know, because the universe will become unreadable in time. We followed it to the deepest edges of physics, the quantum vacuum that makes even empty space energetically complex, the holographic principle that might encode void interiors on their bounding walls, the eternal inflation that might explain the cold spot as the scar of a collision with another universe. And we followed it, finally, to the heat death, the ultimate void that is not the background against which the universe plays out, but the destiny toward which everything is heading. The voids we see today are previews of eternity. The cosmic web is a brief and beautiful exception. What does the current scientific consensus say about all of this? Cosmologists agree that voids are real, they are universal, they occupy the majority of the universe by volume, and they are growing. They agree that voids represent the extremes of underdensity that emerged from the same primordial quantum fluctuations that produced galaxy clusters and filaments. They agree that dark energy dominates void interiors, making voids the most powerful laboratories for testing dark energy theories. And they agree that void anomalies, the excess cold spot temperature, the anomalous expansion rates, the warm intergalactic medium, and the curious void galaxy populations are real observational puzzles that current models do not fully explain. What remains genuinely unknown is almost as large as what is known, the exact nature of dark energy, whether it is constant, evolving, or fundamentally different from any current model. Whether the Hubble tension will resolve to systematic error or genuine new physics, whether the Eridana supervoid's cold spot anomaly reflects a mundane limitation of our surveys or a window into the multiverse, whether void galaxies are shaped by dark matter substructure we cannot see or by some other physics we haven't yet discovered. Science, at its frontier, is always like this. The answers we have create the scaffolding for the questions we now know to ask. A generation ago, we didn't know voids existed. A generation hence, we may understand them well enough to read the history of dark energy in their shapes, or to detect the imprint of neighboring universes in their coldest spots. What this story ultimately teaches us is that emptiness is not simple. The universe's empty spaces are not passive, not featureless, not irrelevant. They are active, structured, evolving environments that shape the galaxies at their boundaries, archive the universe's expansion history in their sizes, reveal dark energy's nature in their dynamics, and preview the cosmos's ultimate destiny in their ever-growing dominance. We have spent the history of astronomy looking at the bright things, the stars, the galaxies, the blazing quasars, and we have learned an enormous amount. But perhaps the deepest lessons are written not in what shines, but in what doesn't, in the spaces between the lights, in the silence between the sounds, in the nothing that we now understand is not nothing at all. The universe has been telling us this for 13.8 billion years. We are now only beginning to listen. The universe is vast. Most of it is void. And in those empty spaces between galaxies, in the darkness where nothing shines, where light takes billions of years to cross, where dark energy reigns without opposition, and the quantum vacuum hums with invisible energy, lie secrets about the nature of reality that we are only beginning to suspect, let alone understand. The mysteries are endless. The journey continues.